This is a video about 1.2.4 in Stein's elementary number theory book, and it's about primes that have the form ax plus b, where a, x, and b are natural numbers. And so the main thing that we'll look at is proposition 1.2.5 in this video, that there are infinitely primes that have the form 4x minus 1. So maybe something to think about in this section. We're talking in general, what can we say about prime numbers that have this form? In particular, are there infinitely many primes that have the form ax plus b? And we'll look at maybe what are some conditions on a and b in order to say yes to that question. And what proposition 1.2.5 is just to kind of point us in the direction that, well, for a particular a and b, when a is 4 and when b is -1, so maybe I should have said in the very beginning that a and b are allowed to be integers. Anyway, though, for a particular choice of a and b, I can show that there are infinitely many primes. But what I skipped over was, it's not true for all a and b necessarily. So in particular, right, what if a and b were both 2? Well, then you could always factor a 2 out of that. Therefore, this number is not prime. It's 2 times something. You factored it. In fact, it's only prime if x is equal to 0. So it's not prime for any natural number x. So we're hopeless to say that this is always prime, and that's not what the result is. So let's look at, again, some particular cases for a and b. So let's look at 4x minus 1 here. Now, just to get an idea about why might this be true, what if I started listing a bunch of numbers that have the form 4x minus 1, and I see that, well, I get a bunch of them when I start listing them out. And let me tell you another reason why it might be plausible that there are infinitely many of these primes. What did we show? What did Euclid show? And we talked about this in an earlier video. Euclid showed that there are infinitely many primes. And that's one fact. And another fact is maybe from a proofs type of class. Let's talk about equivalence classes. Mod 4. And so what do I know? I know that all, how do I want to say this? All y in z are either, or maybe I should say are in one of the set of all numbers that look like what they would look like. They all have the form 4x plus 1, 4x plus 2, and 4x plus 3. So those are all the possibilities for what any integer can look like. They have to fit into one of these descriptions. They have to be equal to one of these. And so maybe you remember what I'm trying to say to you is I'm trying to say that y is in the equivalence class mod 4 of 0, the remainder is 0. The equivalence class of 1, meaning the remainder is 1 when you divide by 4. What else? The equivalence class of 2, meaning the remainder is 2 when you divide by 4. Or the remainder is 3 when you divide by 4. And maybe something that you remember as well is the remainder being 3. That's the same thing as minus 1 here. So if you think about all my primes, if my prime, there's only one even prime, it's 2. And so for my numbers like 4x plus 2, this equivalence class of all, my natural numbers say, it doesn't have any primes in it at all, right? We could factor a 2 out of it. And this doesn't have any primes in it at all. So when I'm highlighting in red, I'm saying kind of forget about it. So if there are infinitely many prime numbers, what I'm trying to get at here is that, well, they've all got to be between these two equivalence classes that are in orange. So maybe it's plausible that, yes, at least 4x minus 1, there should be infinitely many primes that are in there. I'm not saying every number that has the form 4x minus 1 is prime, but I'm saying that there are a lot of prime numbers in that particular equivalence class. So again, that's kind of a proofs kind of way to think about it if you're coming out of an intro to proofs class and you've seen some stuff with equivalence classes. So I hope that made a little bit of sense. And let's go into the proof of it. And what's the idea? It's a neat proof. It's kind of similar to how Euclid proved that there are infinitely many primes, where I'm going to assume by contradiction that there are finitely many, and then we're just going to construct a new one that's not in our list. And so let's do that then. So let's suppose that there are only P1 through Pn are the only distinct primes that I know about that have the form 4x minus 1. So what we're going to do again is we're going to build this new number, n, which is 4 times my list of primes that have the desired form, and then I'm just going to subtract 1 at the end, which you see in the expression for n here. I'm not saying n is prime, right? N is not prime necessarily. I'm saying take the primes you know that have the form 4x minus 1, multiply by 4, and subtract 1. We're going to analyze this number n in order to get a contradiction here. So the first thing to notice is none of these p's can divide n. And if you think about why that is, go ahead and add this 1 to the other side. One way to see this, I guess, is if you add 1 to the other side. Not sure what's going on with my pencil. So n plus 1 is equal to 4 times p1, blah, 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 pn. Well, this in blue says that all the p's divide n plus 1. So it's not possible that the p's could divide n and the next consecutive number n plus 1. So that is what we're saying here. None of the p's are allowed to divide n. None of these p's are. Now the next thing we want to convince ourselves of is that not every prime in the prime factorization of n can have the form 4x plus 1. Now, why am I considering that? This was me talking about the other page. Any prime number is either of the form 4x plus 1 or 4x minus 1. And now we're saying that not all of them in the prime factorization of n could be of the form 4x plus 1. Now let's think about, maybe I should use a different color. Let's think about why that might be true. And I just keep picking the same colors, don't I? So not every prime can have this form. So how come? Well, what if it did? Well, then n would look like, my first prime would look like, I'll write it this way, 4x1 plus 1, and then x1, 4x2 plus 1. So I'm writing out how does n factor into a product of primes. So each of these things in parentheses is a prime. So 4xk, let's say there's k primes in this factorization here. Now think about what if you were to FOIL all this nonsense out. And I'm not going to do it, but what I hope you see is everything except for when you FOIL the last terms out, that's going to give you a plus 1 at the very end of this. And if you think about it, when you multiply all that other stuff out, you're going to be able to factor a 4 out of it. So it's going to have the form 4 times some nonsense plus 1. So in that case, what does that mean? Well, what does this equation say now? N has the form 4x plus 1. That's not possible though. Look at n. It definitely has the form 4x minus 1. So that's not possible either. So what I hope that we agree upon so far is that any prime, so maybe I should say it this way, for the primes that divide n, at least one of them has to have the form 4x minus 1. So at least one prime has to. And maybe there's one more thing that I need to tell you to justify that to you so far, is that this number n is going to be an odd number, right? So I know that 2 doesn't divide it. So that's how I know each of the prime divisors of n is odd, and that's how I know that at least one of them has to be 4x minus 1 by what we just did, that not all of them could be 4x plus 1, and we don't have any even ones. All right, hope you're with me so far still. And so now what we're going to do is we're going to look at, I know that I've found a prime divisor now that has the form 4x minus 1. Now let's try to relate this prime p. Is it secretly one of the p's that was supposed to be, all the primes of the form 4x minus 1 that I know about? So we need to convince ourselves that we found a p that's distinct from these n primes up above. And in this case, this p cannot be any one of those. In particular, how come? Well, because that prime p divides n, and I know that none of the primes in this list divide n. So that's how I know that p is not equal to pi here. So what just happened? Well, we've just constructed a new prime p that has the form 4x minus 1 that did not live in our list. And so the point is that that's a contradiction, and we could do this process indefinitely to keep constructing a new prime that's not in our list that we have on hand, and therefore there are infinitely many such primes of the form 4x minus 1. So again, I'm not saying that every number of the form 4x minus 1 is prime. I'm just saying that there are infinitely primes that have that form. If I scroll down a little bit to generalize this, so that was an instance of, maybe I'll scroll up a little bit. That was an instance of, let's look at primes that have this form for a particular a and a particular b, and maybe you want to know what's kind of a more general result besides just looking at a as 4 and b as -1. So the more general result is this huge theory by Dirichlet, and it's down here, and we just put it in here, or I didn't write the book. Stein just put it in there because it's a pretty foundational result in number theory. So if you've got two integers here whose greatest common denominator is 1, or greatest common divisor is 1. And another way to say this right here is this says that a and b are what's called relatively prime. And you've probably heard that before. So if a and b are relatively prime, then yes, there are going to be infinitely many prime numbers that have the form ax plus b. And so I have, again, the proof of this is just a little bit too much. A little bit too much, but it doesn't do it justice. It's a very, very deep theorem, and it uses some tools that we do not have on hand and that are not easy to necessarily ascertain. Of course, that's an invitation to you to go look. The proofs, there are many proofs freely available. I'll put some links in the description to some lecture notes if you're interested in that. Maybe the last thing that I'll do about Dirichlet's theorem, I'll just pull up the Wikipedia page on it. And what is interesting to me anyway is a little bit towards the bottom on these arithmetic progressions, just to list out a few. So like, what are all the numbers of the form 2n plus 1 look like? And then in the middle column, you see that, well, these are the first 10 of the primes that have the form 2n plus 1. And it's just kind of a cool list. There's lots of cool stuff on this Wikipedia page, again, if you're interested in that.